Yes, we can.
Okay. All right. Good. Right. So we proceed. I think last time we stopped until this slide. This is the second last slide that we stopped. So we'll start from here and then onwards. Yeah. Right. So in this slide, basically, okay, previously we have learned how to what we call derive the equation that relates between duty cycle, the big D, with output voltage and input voltage. So for buck converter, your D will be equals to Vs, or sorry, V naught over Vs. Your V naught is your output voltage. Okay, your Vs is your input voltage. Okay, remember, in order to come up with this equation over here, we have the delta, we're using the delta IL equation. We have two, right? Two delta IL equation when your switch is on and when your switch is off. And then we use the KCL to sum these two equations together, and finally we be able to get the duty cycle. Okay, so next, we're going to then the second equation with regards to the current, which is IL. Okay, IL for buck converter will be equals to I naught, your output current, which is we are using Ohm's law, V over R. Okay, why is that this IL which will be equals to I naught? Because of this circuit over here, where we know that the voltage across your capacitor will be the same as our output voltage, right? So we can omit this. So we take out this path over here. So we omit this, and then we can and then this circuit here become like this, which is our input voltage connect with your inductor and your load. And we can see clearly from here, this is your IL, right? This is your I naught. So your IL will be equals to I naught, provided the components are all components are ideal, which is there are no losses along the way. All right. Okay, next, um we're going to go for the third equation, which is we need to find this one here, IL max, maximum inductor current, and also minimum inductor current. How are we going to find this maximum inductor current? Is that by using the help of this diagram over here. Okay, this is inductor current equation. Okay, which is current versus time. Yeah. So we do it for one cycle. For the x-axis is time. So 0, dt, and t. Remember your wait, okay, this one over here. T on is your the duration for your switch to be turned on will be equals to dt. T off, duration of your switch is turned off, which is it will be equals to 1 minus t times t. This part over here, T on and T off. Okay, the y-axis is the amplitude of your current. In this case, is our inductor current. So in this inductor current, it has a variation. Yeah? So this is the minimum inductor current and the maximum inductor current. The maximum inductor current is also called as, oops, no, wait, is also called as peak of your current. Um, wait. Um, how to get rid of this? Oh, okay. Okay. So if let's say that in the question, mentioned that the peak of your inductor current is equals to certain value, that means that your peak is actually your maximum current. Okay, peak is the maximum point of in this case is current. If let's say that you are looking at voltage waveform, it will be voltage, the peak of your voltage. Okay, in order to find this maximum inductor current, okay, we need the information of average inductor current, which is average. Okay, average is measured from the ground to the center, the not the center, the half of your waveform, or more or less half of your waveform here, which is approximately at this point. So from 0 to this, the middle of your waveform is your average inductor current. So you know that from this value, from the 0 here, the 0 to half of your waveform is your average inductor current. So you have the remaining here. Okay, these remainings, it will, in order to find what is the value for the remaining area, okay, we will use the help of this delta IL. So delta IL is actually the variation of inductor current, which is from what we call from minimum to maximum. Okay, so looking from here, this part over here is actually half of your delta IL. That is why this part over here will be representing by delta IL over 2. This part over here is actually your IL. So in order to find your maximum inductor current, you just add up these two together. IL plus delta IL over 2. This is your maximum inductor current. Okay, now we substitute. What is our IL? So remember in the previous equation, your IL will be equals to I naught, which is will be equals to V naught over R. So okay, we substitute this one over here, V naught over R. Okay, and then plus delta IL over 2. Why is that over 2? Because it only half of your delta IL, not overall of your delta IL. Okay, delta IL, you have two equation. If you can recall back during our session on Tuesday, so we have these two equation, which is when your switch is on, and this one here when your switch is off. Okay, like I said previously, you can take any of these two equation, but take the one with the least unknown parameter. So this one over here. So we use this equation over here, but you need to ignore the negative sign over here. So the negative sign will not be included in the IL max equation. So that is why IL max will be equals to V naught over R plus delta IL over 2. So substitute this one here in the delta IL equation. So it will lead you, your IL max will be equals to V out over R plus V out multiplied by 1 minus T times T over 2L. Okay, next, we take out the V naught here, because we have V naught here and here, right? So we can take out. So it will be like this. Okay. Okay, the T, the big T over there is your switching time. It will be equals to 1 over your F. Okay. F here is your switching frequency. So normally it will be given in the question. What is the switching frequency? Right? So that is the equation to find maximum inductor current. Okay. To find the minimum inductor current, okay, basically we will use the same equation as IL max. The only difference is that we change the sign. So for minimum inductor current, it will be okay, IL minus delta IL over 2, which is, if we substitute the equation, V naught over R minus V naught 1 minus T times T over 2L. Okay, so this is your minimum inductor current. Okay, so and then we go for this is the fourth equation. Okay, then the fifth equation. Okay, wait, I want to show you. Okay, this circuit. Okay, never mind, we can refer to this circuit. Okay, so so now we know the quantity of our voltage and current. Next, we need to find the value of your passive component. So you will need to find what is the value of inductor, what is the value of your capacitor. Okay, although it's being ignored in the analysis, but yet the original circuit, it do have the capacitor. So you need to know what is the value of the capacitor, as well as your load over here. Okay, so next, we need to find what is our value of our inductor. So value of inductor. Okay, to find the value of inductor, there are two ways. We call it as first approach and second approach. So we look at the first approach first. Okay. Okay. We have two approach. First approach and second approach. Okay. Before using any of these approach, okay, you need to know what is the minimum value of inductor that ensure the converter is operating in CCM. CCM, remember, continuous conduction mode, whereby the current is always positive. So you need to find, okay, what is the minimum value of inductor in order CCM mode of converter. Okay, in order to do that, okay, we need to use this IL min equation. So this IL min equation, because this is minimum inductor current, so it will be able to use this equation to find our minimum value of inductor, which is this one here. So let's say we rewrite back the equation. Okay, so this to find minimum value of inductor, you need to set this equation equals to 0, which is we assume our minimum inductor current is equals to 0. Right? So let's say we rearrange back the equation, yeah. So V naught over R. So we bring to the side, will be like this, right? Okay, you need to find the L. So you need to rearrange so that the L will be here. V naught multiplied by R multiplied by 1 minus T times T. Okay, and then you bring down to V naught. Correct. Am I right? Okay, L is up there. 2 is maintained here. V out is down. R is down. Okay, and then so we have common terms, right? It can be cancelled out. So it will lead us to KR 1 minus T times T over 2. Or R1 minus T times T over 2 FSW. Okay, I replace T by 1 over F. Okay, so this is the equation, which is L min. Okay, which is the minimum value of the inductor. So this L min is actually what we call as the boundary of CCM and DCM. Okay, so let's say we have the current. Okay, let's say I redraw the current. So when we set IL min equals to 0, so your current will be like this. Okay, this is your IL min, this is your IL max. So this is the inductor current, yeah. Okay, this is, if let's say that you discover this waveform, okay, this is what we call as the boundary condition, yeah, ataupun boundary mode. Okay. Okay, if let's say that you have the current that in positive side, okay, which is you have a positive IL min and positive IL max. Okay, your converter is operating in CCM, which is continuous conduction mode. Okay, if you find your current going to negative, but later on I will explain, your current cannot go to negative because you have the diode will block you from going to negative, but your current will look like this, where it has the discontinuous part here. Okay, so this is still in one cycle, but has, this is where your voltage equals to 0 and your current is equals to 0. Okay, so this converter, your converter will be in DCM, which is discontinuous conduction current. Okay, so we look again on the waveform later on during your lab perhaps. Okay, so just focus on the equation first. Okay, your L min will be equals to R multiplied by 1 minus T times T over 2, which is come to this equation over here. Okay, this one here, it replace your T with 1 over F. That's why you can you be able to get this equation down here. Right. Okay. Okay, next. In the we call a buck converter, we have another one of passive component, which is the value of your capacitor, right? So now we are going to find the value for the capacitor. How to find the equation for the capacitor? First of all, we need to know what is the function of having a capacitor inside this DC to DC converter. Okay, so this capacitor, all right, is used to minimize the fluctuation. Okay, capacitor. Fluctuation of your output voltage. Okay, so it so that your output become a bit more steady. Right. So normally for any DC to DC converter circuit, the capacitor is normally a bit large in terms of the value, so that the function is that we'll be able to make sure that the output voltage will remain constant. Okay, when the capacitor is big, it be able to maintain the output voltage at our load side to be almost constant. Right. Okay, and then okay, look at this. Okay, this one here is actually your VC, your capacitor voltage, which is, it will be equals to your output voltage. Why is that? Because it's parallel, right? Remember, parallel punya connection. Okay. Okay, this one over here, I want to show you this part over here. Okay, this one here is the capacitor, the minimum capacitor voltage, and this part over here, the peak of the capacitor voltage. So you have minimum and maximum capacitor voltage. This one here is the average. So it will be equals to our V out. Okay, V out average. Okay, right. So again, so if let's say that you want to find what is the variation, okay, so it will be delta VC. So your delta VC will be VC max, maximum capacitor voltage, minus minimum capacitor voltage, or since your capacitor is connected parallel with your output, it will be like this, yeah. So I write a bit down. So V out will be equals to V out max minus V out min. Right. So this is the from this capacitor voltage waveform, you'll be able to get this information. Yeah? So if let's say the capacitor voltage will be equals to your output voltage V out. Right. Okay. In order to find the equation for your capacitor, we were going to use the charge equation, which is Q will be equals to C multiplied by V naught. So from this charge equation, and also we taking into account the output voltage ripple. Okay, this output voltage ripple is this one over here. The output voltage ripple is actually, okay, never mind, I'll write it here. Okay, this one over here. Okay, this is output voltage ripple. This is called output voltage ripple, which is delta V naught over V naught. Output voltage ripple. Okay. So by using charge equation and output voltage ripple, we use this information over here, and these are the derivation, which is you need to find the area under the curve for this waveform over here. Okay, and it will lead you to this equation down here, which is your capacitor C will be equals to 1 minus D over 8 multiplied by your inductor multiplied by output voltage ripple, okay, multiplied by your switching frequency to the power of 2. Okay, your output voltage ripple normally is defined in percentage. So let's say it would say your output voltage ripple maybe so normally it's less than 3%. So maybe your output voltage ripple is, let's say, 1%, 2%, 0.5%, and something like that. So it's normally being defined in terms of percentage. So if let's say that you want to use this information of output voltage ripple, change to the using the decimal value, which is 1 divided by 100 or 3 divided by 100, whatever that being specified in the question. Yeah. Right. Okay. Right. Oh, lupa. Another one yang ini second approach. Oh, I did, okay. I forgot to mention on the second approach. Okay, I will mention in the empty slide after this. Yeah. Right. Okay, now we go for the design consideration for DC to DC converter. Okay, this design consideration is applicable to all DC to DC converter. It can be applied to buck converter, it can be applied to boost converter, and also buck boost converter. Right. Okay, the first point is that the choice of switching frequency, inductance, and output voltage ripple are important in order to ensure continuous current and smooth output voltage. Okay, continuous current, which is in CCM, okay, which is we want in CCM. CCM will be what we call, will be determined by the value of your determined by inductor, the value of your inductor, which is you have the L min. Remember, L min will define the boundary. So you need to make sure that whatever value that you are using must be greater than your L min, so that your converter will be operated in continuous conduction mode, where your current will always be positive current. Okay, and then to find the inductor as well as your capacitor, you will need to use the information of your switching frequency, right? Okay, and then for smooth output voltage, okay, this one over here will be determined by the value of your capacitor. Okay, this one over here, capacitor, this one here will be determined by inductor. So you can what we call substitute the value of your capacitor and make sure that when you test it in the simulation, let's say, you'll be able to get rid of the fluctuation at your output voltage. Okay. The second point, as we increase the switching frequency, the minimum the minimum size of inductor and the minimum size of capacitor will be decreased. Okay, so as your our switching frequency is increased, okay, L mean, the value of L mean will be decreased and the value of C will be decreased as well. Okay, why is that? You can refer back to the equation of L and C. So you can see your switching frequency is at denominator side, bahagian bawah. So when you increase the switching frequency, it will result in smaller value of your inductor and your capacitor. Right. Okay. Third point. Okay. When you with increasing of switching frequency, it will lead to higher switching losses. So you increase your switching frequency. Okay, your switching losses will increase as well. Okay, why is that your switching losses is increasing? Because with higher switching frequency, your punya switch will be turned on and off very, very fast, right? So when the switch is on and off very frequent, it will lead to losses. Okay, and then with higher switching losses, okay, uh, it will result in heat. Heat will be produced. Okay, so when there is heat, it will degrade the efficiency. So you will increase heat for your circuit and your efficiency will be reduced. Okay, and in order to improve this efficiency of the computer, we will use heatsink. Remember, I think you learned during the thermal management where you have the you need to put a heatsink in order to properly manage the amount of heat that being produced from the circuit. So these are the relation, right? Okay. Again with regards to switching frequency. Okay. So this is with regard to the range of switching frequency that you need to use, which is, so normally we will select your switching frequency to be greater than 20 kilohertz. Why? Because of this one here. We want to avoid audio noise. Okay. And the range you can extend up to 1 megahertz, no problem. But be careful, remember, as we increase switching frequency, switching losses will be increased as well. Right. So normally the in order to design the converter, they will like the safe, not that safe, the which is the typical use the typical value of switching frequency is to be at 50 kilohertz, so that although the losses is there, but it's not that many, not that much, and also we'll be able to avoid the audio noise. Okay, right. Okay, 1 2 3 4 5. Okay, point number 5, which is with regards to inductance. Okay, inductor need to be larger than L mean for CCM. Okay, I mentioned here, yeah. Okay, L need to be you need to use larger value than the calculated um, minimum value of the inductor, so that you'll be able to get a continuous current. Okay, so how much how I mean like how, so if let's say that you want your almin, is it like 20%, is it like 50% of your almin? So they don't have like a definite percentage on how big your inductor can be, but normally we will design the inductor to be 25, at least 25 larger than L min. Okay, which is L will be equals to 1.25 multiplied by L min. Okay, 25% larger, which is, let's say we take the ratio of L and L min 1 to 1 ratio. Okay, let's say like this. Okay, 1 to 1 ratio. And then, okay, and then from this statement, it said that 25% larger. So you need to have 25% larger. Your L need to have 25% larger, which is 0.25, right? So 1 plus 0.25 is 1.25, right? So that is why your L is at least 1.25 multiplied by L min. Okay, this one here is actually the first approach. Okay, the second approach, which is we use delta IL equation, where we set your delta IL equation to be at least 40% of the average inductor current. Okay, again, this is not a fixed value. This percentage is not fixed. You can have maybe 25%, 30%, 50%. So it depends. Yeah. But commonly, this is a common percentage that we use to find the value of inductor, which is delta IL to be 40% of your average inductor current. Okay, the last point adalah with regards to switches. Okay, so in order to, you can use any type of switch as long as this one over here, it able to withstand maximum voltage stress when your switch is off and maximum current when your switch is on. Okay, and also you need to take care on the temperature rating, okay, so that it will not be exceeded, or else you need to have additional protection in order to avoid the switch from damaging. Okay, so kita, okay, I summarize again from the, how many points we have, 1 2 3 4 5 6. Okay, so point number 1. Okay, so point number 1 kita. Oh, okay. L, okay, function of L, it will determine the boundary, the modes of operation for your converter. Okay, when L equals to L min, this is the boundary mode. L larger than L min, your converter will be in DCM. L smaller than L min, your converter will be in DCM. Okay. C does not does not determine the modes of operation. The function of C is to smooth out or to minimize the somehow your output, or minimize the ripple. Minimize ripple at the output. Okay. Okay, point number 2. Oh, okay. Okay, we go for this one here. Switching frequency, it should select at least equals to 20 kilohertz, and you can go up to 1 megahertz. Okay, this one, this is set, this switching frequency is set at 20 kilohertz in order to avoid audio noise. Okay, so as you increase your switching frequency, the value of your L will decrease as well as the value of your C. As you increase your switching frequency, the losses will be increased, the heat of your circuit will be increased, the efficiency will be decreased. So this one will require heat sink. In order to manage the heat properly. Okay, next. Okay, the next point will be okay on the value of capacity, value of inductor, right? So for value of inductor, to find L, okay, there are two approach. Okay, first approach is L is 25% larger than L min. So you need to find your L min, then you multiply by 1.25 in order to get L. This one here, CCM lah. Okay. Then for second approach, we are using delta IL equation. Okay. So your delta IL equation, okay, is said to be at least 40% of your average inductor current. So you need to find your IL. So it will be 0.4 of your average inductor current. So if let's say that you need to find your inductor current first, okay, remember inductor current will be equals to your output current for buck converter. So you need to find this. Once you find your average inductor current, you multiply by 0.4, you'll be able to get your delta IL value. So delta IL, remember kita ada dua. Okay, let's say I write this one over here. Okay, so this is L that you need to find. Okay, this delta IL you can take from here. You value it from here. Find your duty cycle, find your time, then you'll be able to find your inductor over here. So this is using the second approach. So both approach can be used in order to find the value of inductor, and both are correct. Okay. 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 Oh, in terms of switch, yeah. Okay. Switches and okay, you can select any switch or diode, but make sure it able to withstand maximum reverse voltage and current. So in order to do that, you need to check the switch data sheet and make sure that you select range that higher than your output voltage. So let's say your output voltage is 50 volt. So make sure whatever voltage, whatever switch that you are selecting, you are using, at least the rated voltage maybe 300 volts or 500 volts, much bigger than the output voltage that been produced from the converter. All right. Okay, so this is basically the sum up from the slide in the previous slide over here. You can anyway you can read through on this later on. Okay. All right. Next. Okay, we go for our example. Okay. Okay. For example, maybe I will give you the final answer for this example here. So I want you to give a try, and next week we will discuss on the solution. Yeah. Okay. So for duty cycle, okay. Okay. First, you need to make sure check first what type of converter that been using in the question. Is it buck converter, is it boost converter, or is it buck boost converter? So in this case, it's buck converter. That is number one. Identify first. Jenis converter. Okay, number two, okay, you check on the parameter or information that been given in the question. So in this one is your input voltage is 50 volt, so your Vs is 50 volt, and then your output voltage V out is 25 volt. Okay, if let's say the name of buck, the what we call the type of converter is not being given in the question. Let's say there is no buck there. Okay, but what you can do is that in order to identify which equation that suitable for that particular converter, look at the information of Vs and V out. If let's say it's a step down, okay, which is your V out is smaller than your Vs, okay, this is buck converter. Okay, if you see step up, which is your V out is greater than your Vs, this is boost converter. Okay. Okay. Right. So if either one, that will be buck is buck boost converter. If let's say step up or step down. Right, and then switching frequency. Switching frequency is 100 kilohertz, and the output power, which is P out, is 125 watt. Okay, you need to find number one is your duty ratio. I'll give you a final answer later on. We'll discuss on this. So give a try so that I can ask any one of you to do the solution next week. Okay, the duty cycle is 0.5. Okay, the value of inductor, so you need to find the value of your inductor. Okay, to limit the peak inductor current. Okay, peak inductor current over here is your IL max, peak kan. Okay, so IL max is 6.25, okay, ampere. So for this one, your L is 50 microhenry. Okay, the value for the capacitor, giving that your output voltage ripple. Okay, so output voltage ripple is this one, is 0.5%. So the value of your capacitor that you will get is 25 microfarad. So these are the final answer. So make sure you give a try, and next week I will call one of you or two of you to do the solution. Right. Okay. Okay, I will stop up to here so that we can be able to continue our discussion next week for this exercise and the subsequent exercise. So is there any question that you would like to ask me before we end our session for today? Ada apa-apa soalan?